This video is all about how we can combine multiple transformations together to represent them with a single matrix. So this question here tells me to transform the coordinate 2, 3 by a reflection in the line y equals x, followed by a stretch on the x-axis scale factor 4. So key things here is that the reflection is taking place first because it says followed by the stretch. So first of all, I want to do this reflection. So I want to remember what the matrix is for a reflection in the line y equals x. Then I can apply it to that coordinate. Some of you might remember what the matrix is for this. If you can't remember, just remember that we could always find it by considering what happens to the coordinates 1, 0 and 0, 1. So if I reflect the point 1, 0 in the line y equals x, this reflects over here and I get the coordinate 0, 1. So that tells me that I have 0, 1 as the first column of my matrix. To get the second column, I need to consider what happens to the point 0, 1 as I reflect it in the line. Well, this becomes this. So this is my second column. So this is the matrix that represents a reflection in the line y equals x. So if I apply that to that coordinates 2, 3, so 0 times 2 plus 1 times 3 is 3. 1 times 2 plus 0 times 3 is 2. So the coordinate 2, 3 gets mapped to the coordinate 3, 2 under the reflection transformation. We can see here that that works. The coordinate 2, 3 gets reflected to the coordinate 3, 2. Right, I am then going to take the result of that and I'm going to stretch it by a scale factor x in the scale factor 4 in the x direction. Remember that can be represented with, remember from the last video, so if it's a scale factor 4 in the x direction, then that's 4. Notice it's not saying that it's being stretched in the y direction at all, so that means that the y has to stay the same. So that means that b would be 1. I'm not going to multiply the y coordinate at all. So this is the matrix that represents a stretch by scale factor 4 in the x direction. So if I now apply that to the result here, 4 times 3 plus 0 times 2 is 12. 0 times 3 plus 1 times 2 is 2. And as we can see here, we do get, as I stretch the point 3, 2 by a scale factor of 4 in the x direction, we do get the coordinate 12, 2. So that was me performing these two transformations in 2 stages. What if I wanted to try and represent that as one matrix? Well, just have a look at this bit here. This came from here. This is the same thing as this. So I could just swap this out for this. That's all I've done here. Just swapping this out for this because they're the same. So I could write these 2 stages as one big matrix equation where I have this times this times this equals this. What I could do, this times this is this. 4 times 0 plus 0 times 1 is 0. 4 times 1 plus 0 times 0 is 4. 0 times 0 plus 1 times 1 is 1. 0 times 1 plus 1 times 0 is 0. So this represents the combination of those 2 transformations. Remember, this represented the reflection in the line y equals x that we did first. This represented the stretch of scale factor 4 in the x direction. And if I do this first, followed by this, I can combine those 2 transformations to be this matrix. As you can see, that does give me the same result here. 0 times 2 plus 4 times 3 is 12. 1 times 2 plus 0 times 3 is 2. So what I've done here is I have represented these two transformations as one single matrix, where the first thing that happened was the reflection in the line y equals x. The second thing that happened was a stretch scale factor 4 in the x direction. Really important, the order here. This is the one that happens first. This is the one that happens second, because the order does matter. If I was to do it the other way round, if I were to do a stretch scale factor 4 in the x direction first, and then reflect it in the line y equals x. So notice that I've flipped these around now. Notice how the order has switched. So this represents the stretch happening first, followed by the reflection here. And as we multiply those together, 0 times 4 plus 1 times 0, 0 times 0 plus 1 times 4, 1 times 4 plus 0 times 0, 1 times 0 plus 0 times 1. This represents that the stretch by scale factor 4 in the x direction first, followed by a reflection line y equals x. And you can see here that these are not the same matrix. So if I were to transform the coordinate 2, 3 by this combination of transformations, 0 times 2 plus 1 times 3 is 3, 4 times 2 plus 0 times 3 is 8. So again, we get a different coordinate than we had before because we're doing different transformations, a different order of transformations. And this still does work. So you can see here I've taken that same original coordinate, but this time I've stretched it by a scale factor 4 in the x direction first to get 8, 3. Then I've reflected that in the line y equals x to get the coordinate 3, 8. So key thing is the order in which we write them. This is the transformation that happens first. This is the transformation that happens second. So let's have a look at an example. So we have a matrix, a transformation U is a rotation 90 degrees anti-clockwise about the origin. So let's try and write down the matrix that represents that first. So remember that the general matrix is the general matrix for a rotation is cos theta minus sine theta, cos theta, where theta is a rotation 90 in the anti-clockwise direction, which is fine, that's what we've got here. So I will have cos 90, which I know is 0, then I've got sine 90, which I know is 1, minus sine 90 will be minus 1, and cos 90 will be 0. So this is the matrix that represents transformation U. Transformation V is a reflection in the line y equals minus x. I'm not sure what that is off the top of my head, so let's figure that out. So the line y equals minus x looks like this. So if I were to reflect the coordinate 1, 0 in that line, it would reflect down here to be 0 minus 1. Ooh, almost got my coordinates the wrong way around there. So that would give me the first column of my matrix. And the coordinate 0, 1 would get reflected down here to be the coordinate minus 1, 0. So this matrix represents transformation V. Matrix R represents transformation U followed by V. So we're going to do U first. So U goes here, V goes here. This is the first one. This is the second one. Then if we multiply these through, so 0 times 0 plus minus 1 times 1, and so on. If we multiply these through, we get that matrix. So this is the matrix R. This is the matrix that represents the combination of these things in that order. So overall, what does this matrix here represent? Like I say, it does represent a rotation 90 degrees anti-clockwise, followed by a reflection in the line y equals minus x. But if I wanted to say what single transformation does it represent, let's look at that matrix there. Let's think about what that means. That's saying that the coordinate 1, 0, which is here, that gets mapped to the coordinate minus 1, 0. So this has gone over here. Whereas the coordinate 0, 1 has stayed at 0, 1. So this has stayed where it is. This has gone over here. So hopefully you can see that this is a reflection in the y-axis. So what we're saying here then is doing a rotation 90 degrees anti-clockwise about the origin and then reflecting it in the line y equals minus x is the same thing as reflecting in the y-axis.